So, a metal ball is fired from a gun, like a bullet, okay, that is powered by a spring that is compressed 21 centimeters. A metal ball with a mass of 64.57 grams is fired from the gun and into a pendulum. Okay, this is kind of weird, but it makes sense for the question. The ball collides and sticks in the pendulum, causing the pendulum to be raised. Calculate the spring constant of the spring used in the gun. Okay, well, let's draw a diagram of what's going on here, because it's kind of crazy. So, really, we have a spring. Let's label this this is like position A. Okay? And we have our ball there. It's being compressed. And when the spring releases, it's going to shoot the ball off. And then we have a pendulum, and apparently this ball comes and sticks into the pendulum. So that's the pendulum, and it's going up. Yeah. So this is position B. So let's actually say this is the spring in the gun, and this is the pendulum. So when the ball is being compressed with the spring, we know there's no movement, so EK is 0 at that point. And EP, and I'm going to put EPS because it's EP, it's the elastic potential energy of the spring. So I'm just going to put that. It's not gravitational potential energy, right? Because this is a spring. So I'm going to apply my knowledge of the springs to this. So this is at max right here. So this is all elastic potential energy. Okay. Then here, when it's swung up, at that point, EK is also 0 because it's telling me it swings up. When it's at its highest point, that EK is 0. And EPG, I'm just going to put the G there to indicate that's gravitational. Now, I'm dealing with gravitational potential energy is equal to max. So then I'm going to put here, this is gravitational. And this is elastic. So I'm just kind of making that distinction. I'm dealing with two different types of potential energy here. But I'm going to assume that this is all one isolated system. Okay? So now, let's also write down all of kind of the other information that we've been given here. So we are told that X, okay, is 21 centimeters. That's the compression of the spring. Remember with our EK equals half, or kx squared? Our x is that distance that the spring has compressed or stretched. So I need to convert that to meters. So that's 0.210 meters. Then it tells me the mass of the ball is equal to 64.57 grams. I need to be in kilograms though, okay? So I'm going to convert into kilograms. Mass of ball is equal to 0.06457 kilograms. And then we were told that the mass of the pendulum, so I'm going to put M of pen, or pendulum, or pen, is equal to 1.5 kilograms. And then we're told the height that it swings up to. H is 9.3 centimeters, which I need to convert into meters, so it's 0.093 meters. So what am I even trying to find out here? Calculate the spring constant of the spring used in the gun. What variable is that? K. Okay. So we got a lot of information to work with here. But we know, since we're assuming this is an isolated system, we can say EM at A is equal to EM at B. So EM at A is equal to EM at B. Because we are assuming we're in an isolated system. We're not looking at friction or anything, so we assume that all of the energy that that spring puts into that metal ball is being converted into kinetic energy and going into the pendulum and up. Yeah. So we're assuming it's a perfect system. So now let's expand each one of these. So at position A, I'm dealing with elastic energy. So I say, okay, well, I'm just going to expand this. EK at A plus EP at A is equal to EK at B plus EP at B. Let's cross off the things we know are 0. So EK here is 0, and EK here was 0. So then I can conclude that EP at A is equal to EP at B. So now we can expand this. This was about our spring. So elastic potential energy is half kx squared. Okay? Because that's all about our elastic. Then this one was about gravitational. Okay, so this one is m times g times h. So what am I actually looking for here? I'm looking for k. So we rearrange to solve for k. Let me just check something. What mass do you think we use? Because we have both mass of the pendulum and mass of the bullet. I mean the thing. So I just want to double check this before. So we have to add our masses together, okay? So we have to add the mass of the ball plus the mass of the pendulum. Okay? So we need to add the mass of the pendulum plus the mass of the actual ball now, because they're both swinging up. So then the answer is 64.734 Newton meters, which then is 65 Newton meters.